Here are two lines of bash that together form a fully functional database. The first function, db_set, takes a key and a value and appends them to a text file. That's it. One line. The second function, db_get, takes a key, scans the file from top to bottom, and returns the last line that matches. Also one line. This is not a toy example. It captures something important about real database design. db_set is extremely fast. Appending to a file is one of the cheapest operations a computer can perform. The file grows, and the write is done. Many production databases use an append-only log at their core for exactly this reason. Appending is fast, and it's sequential, which is friendly to both spinning disks and SSDs. But db_get has a serious problem. Every time you look something up, it scans the entire file from beginning to end. If the file has 1,000,000 records, you read 1,000,000 records to find one. In computer science terms, db_get is O of n. Its cost grows linearly with the size of the dataset. That's a performance cliff that will kill your system the moment the data grows. This is what indexes solve. An index is additional metadata kept on the side that helps you locate data without scanning everything. Think of a book's index. Rather than reading every page to find a term, you check the index and go directly to the right page. But here's the trade-off. The book states clearly and upfront, any index speeds up reads while slowing down writes, because the index must be updated every time data changes. That's why databases don't index everything by default. You choose which columns to index based on which queries you actually run. The cost of over-indexing is slow writes. The cost of under-indexing is slow reads. The simplest possible indexing strategy for an append-only log turns out to be both elegant and used in real production systems. What if, for every key in your database, you kept a note in memory saying exactly where that key's value lives on disk, the exact byte offset in the file? That note is a hash map, keys mapped to byte offsets. When you write a key-value pair, you append it to the file and update the hash map with the new offset. When you read, you look up the key in the hash map, get the byte offset, and seek directly to that position in the file. No scanning. One seek, one read. This is essentially what Bitcask does, and Bitcask is the default storage engine in RIAC, a distributed key-value database used in production. Bitcask's performance profile, high performance reads and writes, as long as all keys fit in RAM. Values can exceed available RAM because each value is loaded from disk by a single seek. The hash map only needs to hold keys and offsets, not the values themselves. When is this the right tool? The book gives a concrete example, a website that stores a URL as the key and a view count as the value. That URL gets incremented potentially millions of times per day. There are a manageable number of distinct URLs, but the value for each changes constantly. Bitcask handles that workload extremely well. Every write is just an append, and the hash map stays in memory. But there's an obvious problem lurking. If you just keep appending forever, the file grows without bound. You'll eventually run out of disk space. And because the file is append-only, you can't go back and remove old versions of a key without special handling. So how does a log-structured database manage disk space? The answer is a mechanism called compaction, and it's more elegant than it might initially sound. Here's the counterintuitive insight at the heart of log-structured storage. Instead of trying to delete or overwrite old data in place, you stop writing to a file once it reaches a certain size, close it, call it a segment, and start a new one. Now you have multiple segment files, each with its own hash map. A lookup checks the most recent segment first, then the next older, and so on until it finds the key. But this alone doesn't solve the disk space problem. That's where compaction comes in. Compaction means reading through old segment files, throwing away all superseded values, every older write for a key except the most recent, and writing a new, smaller segment file. Multiple segments can be merged together during this process. Merging runs in a background thread while reads and writes continue on the existing segments. When the merge is done, read requests switch to the new merged segment, and the old ones are deleted. Now, why use an append-only file at all? Why not just overwrite old values in place and avoid accumulating duplicates? The book gives 4 concrete reasons. First, sequential writes are much faster than random writes on both spinning disks and SSDs. Every append goes to the end of the current file, one sequential operation. Overwriting requires seeking to the old location first. Second, crash recovery is simpler because segment files are immutable. If a crash happens mid-write, only the newest partial entry is corrupted and it can be detected and discarded. Third, a background thread can safely read and merge segments while another thread handles live writes, no locking needed, because neither thread is modifying the same file. Fourth, merging avoids the data fragmentation that accumulates over time with in-place updates. Hash indexes have 2 real limitations to keep in mind. Every key must fit in RAM. You can't have more distinct keys than your RAM can hold. And range queries are completely inefficient. You can't ask, give me all keys between key_1000 and key_2000, you have to look up each key individually. Those two limitations are exactly what the next storage format was designed to eliminate.